Hey, good afternoon. Welcome to class. It's regrettable that I'm not able to be there in person at U of S to deliver this course to local students. And I appreciate people this week bearing with my constrained schedule. I'm running an event here at the Banff Institute for International Research Station, and him trying to work around my leadership of this event. So this week, we're going to be continuing on some themes touched on last week, but with a particular focus on aspects of mobility in agent behavior, including mobility within the context of geographic information systems. This is a theme which we started on Monday. I trust that everyone would have seen the announcements asking you to review a video and one that focused on the impacts of agent mobility. So when we situate agents in space and we undertake mobility on them, the results can be profoundly different than if we explored the same model with the agents situated also in space, but absent mobility. Mobility can often accelerate progression of spread of contagion of various sorts. It could be pathogen, it could be ideas, innovations, knowledge, rumors, attitudes, beliefs, knowledge. But mobility can offer many other impacts as well. Can induce many other impacts. Mobility is often key for seeking access to resources. It brings people together who might otherwise be physically separate. It serves as a sort of coordination mechanism that can lead to big implications for agent-agent interaction. Now, I'd asked you to view that video and the announcements on Monday. Today, we're going to be expanding on a portion of that, focused on geographic context and with a particular eye towards geographic mobility. And by extension, I'm going to be speaking about the collision, as it were, the combination of geographic information systems on the one hand with agent-based models on the other. This combination of rich geographical data on resources, risks of exposures, and barriers and facilitators to movement, etc., geographically, when combined with agent-based models designed to be empirically grounded enough to situate agents within a geographic context, can yield profound limitations, whether it's simulating the movement patterns of animals over a landscape, broader ecosystem dynamics within that context, whether it's aspects of human mobility and access to resources, whether it's care seeking and availability of interventions or treatments, and indeed interventions that are geographically situated. Or if you're trying to build up a model whose behavior is geographically situated and you want it to report for different regions, rural regions, certain urban regions, etc., some sort of outcomes. Having this sort of geographic specificity can be very valuable. Can help on many many areas. It can also help provide some avenues for calibration. So beyond mobility at a more abstract level, mobility within geographic contexts offers some big advantages. And to help illustrate this, I'm going to be doing two things. First of all, today we'll be going through just a brief exposure to a model that I've posted. And I would ask you to go grab it right now. The GIS food and PA, that's physical activity environment with scatter plots version 7. I posted it to each of the learning management systems, and I invite you to get it. And we're going to be talking about some of the, in addition to getting a bit of exposure to the running model, we're going to be talking about some of the principles underlying the motivation for this, etc. And just making notes of considerations when building these sort of geographically situated models. Tomorrow, Thursday, we'll be going over the first just initial steps of actually building up a model with geographic context within any logic, so that agents are circulating within a geographic environment. And the time will not afford us, the hour assigned to us tomorrow, won't afford us the opportunity to take that to its fruition, but it will get you started with the opportunity to experiment by your own hands, building up a model of geographically situated agents. And if you're interested, you can take it much further, and I'll be commenting a little bit on that tomorrow. So those are two plans I have, and I'd like to now turn to that model I asked you to build. And to that end, I'm going to share my screen. Okay, so this is this GIS. I'm going to close all other models. GIS food and physical activity environment with scatter plots v17. It is on the learning management sites. If for some reason you can't find it, I would note that it's in the hybrid models folder within the broader modeling library that I provided you. Okay, let's just expose ourselves briefly to this model. And I want to see its dynamic behavior. So within this model, we have a environment. It's geographically centered in a certain region. The region happens to be Melbourne, Australia, where in 2015, I built up the sort of first iteration of this model. And we have within this model a representation of a number of types of resources and entities. So we're going to have people, which are shown in kind of a Weebles-like little sort of a depiction that looks a little bit like this thing. They have a head and a sort of stylized torso. Beyond that, we're going to have supermarkets shown in yellow. We're going to have convenience stores shown in, that's these small screen green retail-like outlets. And we're going to have parks shown throughout here. Now, what's notable is that these stores are situated at actual geographic locations. The parks are situated also at geographic locations. And by contrast, the agent homes will be scattered throughout the Melbourne city limits. Now, I don't have time to go into the mechanics of the model in detail, but I do want to emphasize where it comes together with geographic information. So basically, individuals in this model, we're tracking the impacts on obesity of aspects of the food environment in a geographically situated context. We track people's weights and their energy expenditure, both basal and sort of due to physical activity. And people engage in, importantly, food-seeking behavior. And that food-seeking behavior considers their preferences as well as distances to stores. And we have some characterization of their probability of visiting a particular venue, a particular store, be it a supermarket or a convenience store, based on the strength of their preferences in the distance of said store from the domicile, the home of the individual agent. So the agents are situated in certain homes as their home base, and using the geographic information system environment here, we can ask for the distance between a given agent and potential stores. And so when an agent starts to seek out food, they have a certain probability of, as we say, shopping wisely. And that probability of shopping wisely here, per comment, takes into account distance to the nearest convenience store or nearest supermarket, and it considers their preferences, and it returns some probability estimated by a consideration of both these two, that they will that they will go to a supermarket. If they don't go to a supermarket, the view is they will go to a convenience store. They'll head to the convenience store, traversing that distance that was calculated here, calculated based on geographic considerations. They'll head there. They'll go to that store. They will engage in purchasing, and then they'll return home. Now, when it comes time to actually eat a meal, they also engage in a decision-making process that reflects their preferences for different types of food, as well as their larder, the amount of food they have of each sort available to them. If there is no food in the home, they'll go shopping for it. If they have only one type of food, they'll consume said food. If they have both types of foods, they will choose according to their preferences, as I recall. And here, this is flip a coin according to their preferences, where they have a certain preference for convenience store meals, pizza pops, and I think meat pies or something in the Australian context. If I'm not saying something called a floaty or floater, I was told in Australia, or what have you, which are somewhat unsavory, ultra-processed concoctions. Okay, and they then sate their taste, but they engage in food shopping behavior, which will trigger them going seeking food and undertake this stage. Right? So they have at any one time a certain number of meals remaining in their larder, convenience store meals, supermarket meals, and we total up how many meals of each sort they took, they consumed, and each meal, based on its composition, has different impacts on their energy intake and thereby their consumption, their energy balance, and thereby their weight. And there's some logic for eating a meal, which makes use of this logic here. It goes off periodically, and and brings them into contact with the need to decide. Okay, so these agents are placed in the space. There are parks, which are really passive entities. They just exist at certain places, and those induce the presence of a park induces or the proximity to a park induces a higher likelihood or higher level of physical activity expenditure. And there's some relationship between the distance to the park and there and that basically induces a certain level of physical activity. So use of parks is considered more or less continuous rather than, in contrast to seeking food from a store, which is considered kind of a discrete action. They go and engage in food shopping, and they purchase foods for their larder at home. Larger amounts from supermarkets, smaller amounts from convenience stores. By contrast here, they're assumed to have a certain level of energy expenditure over time that's dictated by their kind of proximity to a park. Now, this is all placed within this overall environment, with much of it being geographically situated. And what's notable, and so I'd like to invite you to run it. I will warn you, and this will come to our elements of our lecture shortly, that it can be network intensive to get started, as it figures out the routing paths from the actual locations of agents to their destinations. It figures out what's the nearest routing, figures out, by extension, what's the nearest convenience store or grocery store to them, and actually routes them along with it. So I'm going to click on this big population with walks, and I'm going to run it. And just bear in mind that I have a cached version, so I have a version which is kind of preloaded some of this information. For you, it may run slower. Okay, so here we see agents in a sort of Webelian fashion, placed in space. These agents, their girth, their shape, is indicative of their weight status. Okay, and they are engaged in movements around this space to go and seek out food here. Okay, now I zoomed in, and I seem to have we actually had a rather pleasing sort of depiction, but it seems if I'm zoomed in too much, it engages in visual artifacts. So I'm just going to stay at this level. People are moving back and forth between homes, shown in blue, and supermarkets, shown in these colors here, these yellow colors. Again, the small green stores are the convenience stores, and a lot of the time they'll be closer. Now, if we run this, we'll find that, well, there's a lot of vagaries day to day in their movement patterns, convenience store, grocery store, what have you. The proximity to parks, the proximity to stores of different sorts, and their preferences will induce patterns of consumption. And those patterns will bear consequences writ large upon their girth here. So you'll notice that some agents are relatively svelte. Some agents are relatively compact in their side, while others are gaining weight, as indicated by their sort of minor axis diameter. And if we were to run this, we would see actually a disparity develop between those who are closer to convenient or closer to grocery stores, for example, and parks, and have preferences for fresh fruits and vegetables from stores on the one hand, and on the other, those who are in food deserts, who are close to convenience stores but not grocery stores, who have preferences for screaming yellow zonkers or meat pies or pizza pops or other unwholesome types of nutriment, and those who live far from parks. Now, if we sort of zoom around here, what you'll see, and I'll highlight up here, is each dot here is a person. The location of a given dot, its X location, say 0.3, is given by the fraction of their meals that agent has eaten at a convenience store. The Y location of a dot is their weight in kilograms. And what you will see on this kind of zooms out from the helter-skelter of, all these back and forths of particular agents, but you'll see the emergent behavior, right? And so as people eat a larger fraction of their meals at convenience stores, that is, they're further along this axis, and they tend to have larger weight. And it's not without exception, right? If they live close to a park, perhaps they're benefiting from that. If there's someone who has strong preferences for healthy food, that will factor into the fraction of their meals eaten at convenience stores. But, if they're near a park, even though they may eat a lot of their meals at convenience stores, it may be that they can, their weight is less high than one might otherwise surmise. But there's definitely an emergent pattern here, an association between these two metrics. I do want to highlight that this sort of scatter plot is of great value within agent-based models. Being able to see, it allows you at once to see broad associations and patterns on the one hand, but also see heterogeneity at the other. What can be more valuable is when it's possible to color, for example, a dot, or otherwise distinguish it with a shape or what have you in one graph and compare it to the same in another graph. But for now, I'm going to just note some other graphs here: grocery store distance on the x-axis versus weight in kilograms. Broadly, the further they are from a grocery store, there's a slight upwards trend in weight. By contrast, if we compare the ratio, like how far is a grocery store compared to a convenience store? So 4 here on the x-axis would mean the grocery store is 4 times further from the agent's location than the nearest convenience store. So the nearest grocery store is 4 times further than the nearest convenience store. That's on the x-axis, and the weight in kilograms is on the y-axis. And what you could see a more marked upwards trend than is obvious here. It's, this one doesn't take into account the distance to the closest convenience store. And the longer the grocery store distance is, and maybe that, convenience stores are also quite far. Maybe this person is situated in the outskirts of Melbourne or what have you. And, we can look at preferences and how preferences for meals for convenience store from 0 to 1 induce a certain weight in kilograms, etc. Here's park distance on the x-axis versus weight in kilograms. And once again, you can see a kind of dose-response relationship, or inverse thereof. The further the park is from this person's home, broadly, the higher their weight will tend to be. Shown once again through the lens of scatter plots. Okay. So, what we see before us is an illustration of a geographical model. We see agents being, engaging in seeking of resources here in a way that's mediated by distance. We see proximity to certain fixed locations whether it be convenience stores, grocery stores, parks, as shaping their evolution. And we see them, those interacting with preferences. I do want to highlight that models, as we've long emphasized, are tools for reasoning about counterfactuals. And if we kind of scroll down here, go back at some costs to the original thing, we can see, well, if we click here, for example, what's the effect if we place grocery stores in certain areas of a community, for example? How will that change things? So if I place a new grocery store, how will that alter the dynamics? It will provide new choices. It will shorten distance for some individuals from the grocery store, and it may alter over time with some delay, of course, due to the physiological time constants and so on involved. It may alter their weight and their weight trajectory. So I've just placed a new grocery store, and it's actually recalculating everyone's routes to the grocery store, to this new grocery store, trying to figure out, okay, essentially, there's going to be some agents affected, those for whom this will now be the closest grocery store, and it will alter their balance of preferences for grocery stores on the one hand, compared to convenience stores, or for buying food at each, for start up their larder at each, and thereby for eating at each, and thereby for their weight. So if we ran this in the fullness of time, we would see some of the graphs above, maybe less so this one, but ones involving grocery store distance, for example. It would probably shift it to the lower side of this because there's fewer people living in a food desert, etc. Okay, so this is a quick glimpse of a geographic model. We see that it has interplay of the geographic locales and location of certain resources interacting with the agents, and we see that it can feature in some cases in counterfactual interventions, where we move beyond the set of stores located at geographically known locations, and we instead add some in counterfactual locations to see what the effects are induced on agents as a whole, those patterns as a whole, or for different subclasses of agents, different stratifications of agents. So that's a bit of a model. And tomorrow, for those coming to lab, we'll be building up the very start of a model like this, and just getting in place the basics of geographic environment and letting people circulate it. Okay, I'm going to here stop this model, and I'm going to now turn to some slides. Oops, that's not what I wanted to do. There we go. So in previous talks, I had spoken about spatial, the motivations and considerations that come into play when situating agents in space. Here we're dealing specifically with geographically situated and aware models. And there's many consequences of these. There's a potent source of really relevant substantive amounts of data. Geographic information systems are very rich in terms of the type of data they might include, whether it's topography, levels of nitrous and sulfur oxides in the air for health regions, hazardous chemicals in, say, U.S. Superfund site areas, availability of stores and services and green space, walkable streets, etc. Right? Often this is where one of the major avenues where big data comes from models. And geographic awareness can help us reason about the impacts of, interventions at particular hospitals because it relates to the catchment for the hospital. Say the Addictions Recovery Community Health Program run in Alberta by my colleagues there quite successfully. For if you're engaged in large-scale testing, drive-through testing sites, reasoning about regional case numbers, if you're interested in how changes to the street patterns might affect quality of life or exposure to exhaust and other adverse pollutant effects, these sort of models are very valuable. And as many people here are likely to know, geomatics supports deep expertise in this sort of information. I will further note that for reasons that I can't fully explain, but are likely rooted in human psychology, when we include geographic context in models, it often helps stakeholders who might otherwise find models too abstract suddenly connect with models. I can't fully explain it. I've seen it quite a few times and others have reported it. There's something about seeing your community, seeing particular locations you recognize, seeing agents interacting in that environment that can open people's eyes to the promise of agent-based modeling, can help stakeholders have a sense of buy-in or a sense of confidence, or a better sense of the potential for agent-based modeling. I'd alluded in passing to different ways that geographic information systems can factor in, and without trying to be exhaustive about it, I put a bunch here. Presence of GIS can allow us to determine distances of resources, right? We saw that. Agents shape their decision-making based on distance to types of stores, and that allows us to examine the impacts of interventions that might alter those distances, right? Care seeking. If you have to drive 2 hours, 3 hours to seek care, that might materially lower the prospect of you seeking such care. It might delay your seeking care for some imaging where that delay might impact cancer progression or what have you. Other elements of our work have focused on agent exposure. This is more broad, but using our data collection system, agent exposure to messaging, to promotion, tobacco outlets, billboards, ads at gas stations in the US that are allowed to use imagery and promotional materials involving tobacco or vaping. You can capture exposure on the part of agents to these environments if you're situating how the agents move back and forth, right? You can recognize how urban design and street routing and bridge access, affect walkability and thereby hope to examine how it impacts behavior and by extension, health consequences of said behavior. we can work to associate agents specifically with resources, perhaps the nearest emergency room, that is going to govern their care or be the point at which they seek care. More than this, agents might, for example, seek out certain community services based on what's the closest one, or testing sites, right? Other types of uses of GIS would involve having a map where there's records, perhaps likely historical or likely simulated, could be, of levels of particulate matter or hazardous chemicals or radon in the home, and in understanding how that's affecting different agents in a way that allows counterfactuals, right? Asks you, suppose we could have radon abatement in homes, or suppose we could support routing restrictions for vehicles, charge for congestion pricing for vehicles. How would that affect these sort of health impacts for different areas of our city? And finally, I'll note that geographic information systems allow us to reason about how aspects of the physical and built environment shape those movement patterns. If people's buses are routed by areas outside of food desert, which might have ready availability of groceries, for example, it might allow easier access to those than if those are far away and not accessible via public transit. Whether it's physical features like rivers, water bodies, or aspects of the built environment, the presence and absence of barriers, etc., offers some pretty big opportunities for examining impact on agents. Now, I want to talk some about some rather different types of geographically situated agent-based models. And not all of these are mutually exclusive, but often model will fall into different categories, and I've listed some here. A first one is where agents are affected or driven by empirically observed mobility patterns. So here we might have mobility patterns actually measured or characterized as part of transportation studies through GIS data collection on platforms like our Avicenna platform. We actually, have patterns of how agents move in the landscape, and we might, in our model, drive agents according to such patterns. By virtue of doing that, we can then ask, to what are those agents exposed? So look at, consider the amount of billboard promotion of tobacco along that route, or access to food, healthy foods along that route, or exposure to particulate matter along those empirical routes. So here, the empirical routes, the agents aren't making autonomous decisions for this first bullet point. They're instead sort of pre-programmed in their routes, and you are understanding the feed-forward effects. This is not an aspect of a highly endogenous model. Here, we're using agents to specify these exogenously dictated patterns, and we're hypothesizing what the consequences are on agent health, for example, or perception, on behavior, that might not be measured. Maybe it's smoking behavior or vaping behavior. Maybe it's development of COPD or restricted or some sort of lung disease. Um, uh, Another possibility is we have that empirical data, but we have in place an agent-based behavior model for mobility and for movement, for physical, spatial wandering that is calibrated to these patterns. So we have mobility patterns, and we try to get the model to match as emergent patterns these empirically observed ones. Now, here we have extra flexibility, right? The first one, where we have empirically observed mobility patterns, it follows that if those are exogenously dictated, we're not going to be able to examine counterfactuals readily that ask how will mobility change if we put in place this new walking path, this new biking path, this new bridge? How will exposure to ppms differ if we change our transit routing? We generally won't be able to do that because we won't be examining the ripple-through effects on agent behavior of these investments and changes to the built or physical environment. By contrast, the second one, where we calibrate it for historic periods to best match that, maybe based on agent preferences, et cetera, and then we can put in place interventions that will allow us to ask what-if questions, which might change agent behavior, might lead them to have different mobility patterns going forward. So maybe we make transit cheaper or free. Maybe we, again, put in place amenities like bike paths or what have you. So we can here examine changes of behavior. The first one, we could still examine the impacts of some changes, right? We could ask something about what if we put into place new food stores or a new testing site, and we posit that a person's likelihood of visiting it will be based on their empirically driven movement patterns. We might see the ripple-through effects of that testing site or of that food seeking, but we wouldn't be altering their behavior in a way we might for the second, where we change mobility, and we might change mobility behavior going forward. We calibrate it historically to what's there, make sure it reproduces it for those patterns, that we have plausible characterization of the historic patterns, and then we can ask what-if patterns that might change that mobility. A third very tempting path, rather different, is where we have simulation that augments endogenously as the model runs GIS data. So maybe it sheds pollutants into the landscape by changing car patterns. Maybe it sheds pathogen. Maybe we have white-tailed deer being simulated, or mule deer, and we simulate the spread of chronic wasting disease, and they shed prions. And those prions build up and expose other deer within the environment. Such prions are believed to sometimes last a decade or more in the environment. And therefore, when you simulate the model, it builds up this stock, this store of pathogen, which can then expose other agents. So they're the environment. And the presence of certain quantities in the environment becomes a potent endogenous feature. The fact that it's geographically situated matters because it's by shedding it at location X that other agents traversing the landscape near X or at X are exposed, right? And when we augment GIS data, we can undertake that. You could argue a similar thing for simulation of superspreaders in transit hubs or transit stations or what have you. And indeed, we have published work with valued collaborators in China on spread of infection in high-speed rail stations. The last one, I'll note that simulation model is generating data and we compare it to geographic pattern. And so we're trying to build up a model that accounts for that, that helps explain, that provides a sort of theory for data we see historically. Perhaps it's data about health disparities. Perhaps it's data on risks of, for example, incidence of COPD or incidence of lead exposure or prevalence of lead at high levels within bloodstream of children in different areas. So here we're simulating we have an agent-based model, and we're trying to understand what's driving some of these patterns. Like, what is it about the environment? What is it about the mobility patterns? What is it about aspects of the housing stock there? What is about something about the level, the circulation of pollutants or contaminants within the ecosystem or within the air or soil or water? And we're seeking to account for these patterns, presumably because sometimes because we often want to go and because we want to go and ask what if questions. We might ask, what if we could abate these adverse exposures in certain ways? So there are times where we use GIS data, which provides some current level of exposure, and we seek the model to reproduce that, and then often to ask what if questions. Okay, let's talk about GIS models. You'll see as we build up our first GIS model tomorrow, we'll see elements of this. So some common features in GIS models that help further these ways of interacting with GIS models of data in ABMs. Well, perhaps one of the most basics is accessing GIS information from GIS databases, right? We have a GIS database, OpenStreetMaps, for example, or there may be data from geographic information system vendors, such as the ARC products. And we use GIS data from these databases within our models. We saw that in the model earlier, where the imagery or the depiction of the city and the location of resources, et cetera, are from that. Loading of GIS shape files. Here you might have shape files giving information on topography or elevation levels or level of measured nitrous oxide in the air or contaminants in the water or what have you. And you're loading this in via a shape file. Shape files can contain many types of information, and loading them into a model lets you then reason about those types of information within the model, either to compare with model behavior, to have it drive model behavior, etc. Common feature within agent-based models is we assume continuous space, and we're at a high enough level of abstraction and high enough level of summary that uh, we don't assume that agents block each other from traveling via a route. An important exception might be congestion-related models, but in many models, there's an assumption that we're so zoomed out that if an agent crosses this path and another one crosses that path, that they're not going to, the presence of one is not going to prevent the other from traveling. Again, congestion models have their own logic, often intensively GIS based, but also need to get into aspects of perception and, sight, range of visibility. And there's a whole rich area of agent-based modeling, such as by my old colleague Moshe Ben-Akiva at MIT and others regarding these sorts of models. Quite often, agents within these models will have some latitude, longitude. Sometimes they'll have some measure of altitude as well. It could be that might govern certain aspects of their movement. If you're in a built environment with pronounced vertical relief, like in a city with buildings and so on, that might be particularly relevant to take into account. Often they'll have a heading in a certain geographic direction. And there'll be agent location within that latitude longitude space, as well as that space being used to load in resources. There are times, and it's quite frequent, that we will query GIS data within a model's operation for certain information. We saw that in the earlier model, right, that we explored. So agents might ask, tell me the nearest X, right? Or they might say, bring me to that X, like route me to my child's school, or bring me to the nearest testing site that's open at this time, or what have you. There might be other sorts of queries that are sought. Ask about my current level of exposure to some contaminant, or my distance from a billboard, or what have you, or if I'm in a certain line of sight of the billboard. So querying, like based on my current situated location for certain information, is often sought. Could be crime levels, for example, another factor. So per my comments in getting that model running, I want to highlight, and this will play a role tomorrow in a significant way, that use of geographic information systems, use of the features in them, carries a high degree of computational overhead. It's something that needs to be considered early and in a pretty fundamental way when building a model. It tends not to be something you just layer in casually. It impacts computation time, the speed with which the model runs. It impacts the memory used by said models, and it impacts the network use or it often does, because within these models, commonly information needs to be brought in from network databases. They could be databases within your organization. They could be databases that are more general, like OpenStreetMaps, ArcView, et cetera, or those associated with ArcView or QGIS. And here, there is often, not always, but often, a need to go over the network to grab some information. Now, within computer science more generally, and here as a very, an exemplar use case, there's a key value for information that isn't changing live, that isn't recording, a mobility, isn't recording congestion right now or weather right now, which is a potential thing you can do. Ask about the current weather at certain locations, current temperature, current congestion. But if absent that, if what you're accessing is types of information that change slowly, you can get great advantages out of caching, out of having a temporary copy of it that is held locally. When we say cache, we're talking about a localized copy that is designed to be loaded quickly and reason about quickly compared to one that might live in some remote database or be accessible only through a database interface. So caching, like keeping copies of that information, is often key. And the very performance of the model that we've already seen, the fact that it sort of stopped for a while after I added supermarkets and then resumed and sort of went along faster, was a reflection of the fact that it had to figure out anew what's the nearest supermarket, take into account all the routing information on the streets, and oh no, they can't go that way, there's a river in the way, et cetera, taking into account this network. And then having taken that into account, caching it, so the next time agent A is at home and asks, where's my nearest supermarket, it knows immediately where it is because it's figured all this out. Next time they say, bring me to that supermarket, it routes them along the route it already figured out. So this notion of sort of caching, reusing a fast local copy of this information is key. And one of the things you'll find with any logic, just as an example, not to privilege it, is that if we go to a model like this, and I didn't plan to do this, but maybe I will just show so you can see it firsthand. If I go to hybrid models here, where I'm storing this model, and I go to this exact one I'm running, excuse me, here we go. You notice there's a hash, and this cache has the results of route searching and caching of tiles of sort of what's shown at different places geographically in that street map, right? And that information can be stored and then reused very, very cheaply. It can be, not small, right? Like this 41 megabyte file for caching of routes, et cetera. With larger populations, it could be larger yet. So when it comes to GIS, we need to be conscious of cost computational, the resource cost associated with fetching information from data sources and then using it. And we want to take into account if that information is changing slowly compared to the execution of the model, it will generally behoove us to have this copy. Any logic automatically caches that information unless you tell it otherwise, to do otherwise. You can proactively say, hey, get me a much bigger set of information located on my computer, and it can go rip snorting fast, to use a technical term, compared to how fast it would run otherwise. And there's a whole lectures that could be given on how to cache effectively, how to go proactively get that types of information, situate it for very rapid access. And I have students who specialize in that for very large scale age-based models, such as my student Eric Redekop, working with trucker routing data to understand the impacts of availability of services along major interstate highways, particularly in the U.S., on trucker health and the impacts of exposures to food of varying quantities in the execution of their duties as a trucker. Okay, so for those who can join tomorrow, I apologize because I'm running this event, taking time off here. From the event right now, I need to return to it. I'm not going to be able to offer office hours. I apologize. They will resume next week. Those who can join tomorrow, you'll see getting started with an agent-based model, getting it situated so we can have situated agents moving around in space and visiting these sources. That's all for today. Thank you for bearing with me being out of town. I look forward to joining those U of S students locally next week. I'm driving back the 8 or so hour drive on Saturday. But in the meantime, I'll look forward to seeing you for the remaining sessions during the week.